You're taking 3 courses,
Yeah, well, the third one just started.
and you got a full-time job.
Uh-huh, yeah, so I'm insane.
No, but you soon will be.
Well, this course and the first one, they both end next week, so, but the other online course, this is really odd, because all my other terms, when it was spring break for the University of Maryland, it was spring break for the online course, we had the week off. So Ron and I are going to Australia for our 40th wedding anniversary, and the course that starts this week isn't given spring break, and I'm going, seriously? I have to now do coursework in Australia?
How romantic.
I wanna shoot
Who, Ron?
her. Huh? No, it's just, I don't know why, I mean, and this is all through University of Maryland, it's like, did the
I
one
know.
hand not talk to the other hand?
That happened to me last
Yeah.
semester.
I don't know if they're just not talking to one another, but it should be spring break.
No, they're trying to, they have an algorithm to optimize dollars. And
Yes,
this is what it told them to do.
yes, and at the expense of the students' work.
Oh, yeah, absolutely. Absolutely, casualty, total
But,
casualty.
I do appreciate this, but I will have to view the video that you send out for the rest, because,
Okay,
I need to get home and get working
it's
on
okay.
homework.
This is not required, attendance. It's okay.
Well, I get a lot out of it, I appreciate that you did this.
Oh, you contribute a lot too. You really do.
Well, with nonsense, but that's all right.
Well, as a whole course is nonsense, so it fits right in. Okay,
As long as I pass and get my degree,
you're in very
I'm
good
a
shape.
happy camper.
You're in very good shape. See you for Thursday. Bernie, this is impossible in your second language. I fail to not support the opposite of the rejected claim. No, you cannot do this. It's impossible. So don't worry too much about the conclusion, just get the numbers right. Now you worry about the conclusion, it's not your second language.
Yeah. Actually, you don't know that, but
You fake it really well. Sorry, I just have the one, not extra, no. Yeah, we can print out extras from now on, though.
The main problem is the wording, the way to settle the problem. That's why I'm trying to figure out how, like, you read the sentence, you read the question, and I would try to write down my parameters, you know, what all the equipments, what the different stuffs are, and then to really grasp what the question is asking for. You know, I mean, the last usually they will say construct this hypothesis test or whatsoever, but just the you know, the way the world the problem is coming to be able to interpret the actual problem. That's my weak.
Well, it's not your weakness, it's Hilkowski, the author's weakness. She's imprecise, she's loose with her language. And it's not your fault that she's loose with her language, she is. And she doesn't state things precisely and exactly. Triola, the book that we used to use, his problems, you would love them, they're exactly stated. There's no ambiguity. Bilkowski has a lot of ambiguity. So it's not your fault, it comes with a free text. And it makes perfect sense to her because she knows what she's thinking. But it's only after you get up to 4th and 5th edition that you found out that the student doesn't know what you're thinking. And you have to get more exact words. So this is a brand new textbook, she's just writing it, and it's a little rough. So it's not your fault. So just state your interpretation, and after you stated your interpretation, then the important thing is if you do the calculation correct based on your interpretation. That's okay, as long as you do that. Yeah, because there's no absolutely correct interpretation. As on this last one, it could have been interpreted either direction. And I agree that I say that. Yeah. And the way that she meant it doesn't really have to be the way that we do it. As long as you can make it a good problem, just slightly different from hers. So just state your interpretation and full speed ahead. Don't worry about getting the interpretation exactly right. It's not going to happen when she's using loose language. No, it takes years to learn how to open the door. And then you can forget. We're gonna go to Lane. More ambiguity. Actually, Lane is not ambiguous, but he has a lot of fine points that aren't terribly important that he makes a big deal out of. So we're gonna shake up some martinis. Ernie, do you know what is a martini?
It's alcohol.
Alcohol, that's right. Gin and vermouth. So we're all back, we might as well start. You want another minute break? Okay, Kayla still wants more break. Okay, we're on page 396 in Lane, exercises. Okay, number 1. An experiment is conducted to test the claim that James Bond can taste the difference. So, Nux, have we found the claim?
Yes.
So you see how Lane uses much more explicit language than does Ilkowski. He's much more professional in this respect. So the claim is that James Bond can taste the difference. And we always start with the claim. So, what is the anti-claim?
He cannot.
That James Bond cannot taste the difference. So now, let's put this in mathematical language. If he can taste the claim, if he can taste the difference, then what is his proportion of correct answers going to be? Well, let's take it the other way. If he cannot taste the difference, if it's just random guessing, then what's his proportion of correct answers going to be? 0.5, agreed? Gonna be straight down the middle. So this is P is equal to 0.5. And if he can taste the difference, then P is going to be greater than 0.5. Or, good. So now, we know that the null hypothesis is the one that takes what sign?
No, policy.
The equal sign, right?
Policy, yeah, that's the, no, policy, yeah, the equal sign.
The equal sign.
Yeah.
The null hypothesis always takes the equal sign. So what is the null hypothesis in this problem? Is that P is equal to 0.5. P is equal to 0.5. That's what you're going to test, whether P is equal to 0.5.
So the null hypothesis
Can you
is
say-
the an-
Is the anti-claim.
Can the anti-claim also be said, I mean, he could be, can he test less than 0.5? So.
Yes, well now,
he could-
Lane makes that, and about 2 later pages, he makes that point that what you really want to test is not P is greater than 0.5, because let's suppose P turns out to be 0.8. Does that mean he can tell the difference? True?
Yeah.
But suppose P comes out to be 0.2.
He can.
That means he can still tell the difference, he's just confused which drink is which. And that's significant, isn't it? Because that's very far from random chance. So what Lane really wants you to do in these cases is always test unequal, because
So it's.
nature may fool you. It may turn out to be something unexpected, but it's also significant if it comes out to be very low, just as if it came out to be very high. So Lane recommends that you test unequal to 0.5.
It's two-tailed, that's all.
It'd be two-tailed by Lane's suggestion, but he only gets to that 2 pages later. On this page, he's still doing with a right-tailed test. Okay, so next one is number 3. Okay. Number 3, why do experimenters test hypotheses that they think are false? Anyone?
Say, oh, let me
They
read it.
already know it's false, but they test it anyway. Why?
Because there could be an error.
No, they want to see how false. They want to see how false it is. Is it just a little bit false, or is it really ridiculously false? Number 4, state the null hypothesis for an experiment telling whether Inchi-Ashia decreases the length of colds. So somebody tell me the answer. Well, what's the claim?
That it does.
That it does? Well, okay, so now, before it does that, you have to have a population for length of colds. I was gonna have some mu value for the length of colds, agreed? So now you're gonna have your sample. And now, so the length of colds is equal to some number. So let's call it L, agreed? Is the established length of colds in the population, true? Now what you're going to test is that the mean value, now if you have a population that is all Inchi-Ashia, using Inchi-Ashia, you get a mean of mu, agreed? And so what you're going to test is that the mean of the population is going to be less than the mean of the population included in using Inchi-Ashia. The actual group is going to be less than the control group, agreed? You've got 2 groups, test group and control group. and the mean of the test group is going to be less than the mean of the control group, okay? And so the null hypothesis is that mu is going to be greater or equal than the control group, agreed? So you got two groups, a test group and a control group, agreed? And they're each going to have a mean length of cold. So what's going to happen is that the test group is going to be less than the placebo. True? That means that it's effective, it's doing something. But if the test group is equal to the placebo, is this medication effective? But how about if the test group is greater than the placebo? It's interesting, isn't it? So you do want to check that out. So the null hypothesis is that the test group is greater or equal to placebo. You don't expect it to be greater. You don't expect Inshiasha to cause colds, do you? But you might discover it. So the null hypothesis is that it's equal to the placebo, because you want the equal sign for null hypothesis. So the test group length would be equal to the placebo length for the null hypothesis. C, an investigation of whether self-proclaimed psychic can predict the outcome of a coin flip. What's the null hypothesis there? I'll listen to you.
Mu is equal to 0.5.
Is it mu or p? Is it a proportion or mean?
Oh, it's proportion.
So the null hypothesis is p is equal to what?
0.5.
0.5, agreed? If he can't predict it, if he's only getting random results, if he's an ordinary human being, then what percent of the time is he going to be right? 50%, agreed? Okay. Now, the claim, you can say the claim is that p is unequal, p is greater than 0.5, agreed? Just like James Bond. The claim is that he is right more than half the time. So the anti-claim is that he is right only half the time. So the anti-claim is p equals 0.5. And which one do you take for the null hypothesis?
Null hypothesis would be equal.
Exactly right. You're catching on very well now. A study comparing a drug with a placebo and the amount of pain relief, a one-tailed test was used. In other words, they didn't test for something unexpected, and it works just like number A, the one we did on the board. So that's a repeat. And I believe the next question is 8, am I right on that? 5. Oh. Assuming that the null hypothesis is that mu equals 50, and the graph below shows a sampling distribution of the mean, would a sample size of 60 be significant in a two-tailed test? Now, significant means it's in the red zone. The word significant means it's red zoned, okay? In other words, would a value of 60 be in the red zone? So look at the graph and tell me, is 60 in the red zone at the 5% level? It's not even near the red zone, is it? If Karen was here, she would say, well, no, it's very near the middle, so that would do it. So next one is still 8, okay? A significant test is performed at p equals 0.2? 6.
1, 2, 3,
Yeah,
4, 5, 6, 8.
There they are, okay, I just didn't follow my own writing. A researcher develops a new theory that predicts vegetarians will have more of a particular vitamin in their blood than non-vegetarians. An experiment is conducted and vegetarians do have more of the vitamin. Is that the end of the discussion? But how much? But the difference is not significant. In other words, it's not in the red zone. True? The probability value is 0.13. And usually the red zone is around 0.05, agreed? Or 0.025? So this is significantly in the do not reject zone. But should the experimenteer's confidence in the theory increase, decrease, or stay the same? The probability value is 0.13. Now, what would you, now, even though you're not in the red zone, you can get a inclination of direction, a tendency, agreed? In other words, if you're very close to the red zone, is that a warning?
Yeah, that's one.
Now, is this close to the red zone? 0.13? Well, what's the z-value for 0.13? Use your table. What's your z-value for 0.13?
Red zone?
No, not in the red zone, just a z-value for, put 1.13 in the body and get your z-value.
19082.
No, go into the body. 0.13 is in the body, and then read off, yeah, 0.13 is in the body. So what's the z-even number?
Closest is probably
Yeah, closest.
-0.13.
0.13. Okay, now, this value is,
1.13.
this value is 1.3 standard deviations.
1.1.
Okay, 1.1. This value is 1 standard deviation off the center. Okay? So, is that supporting the claim, vegetarians do have more of the vitamin, 0.13, and, so is that supporting the claim that they do have more? If it's only 1 standard deviation away?
Yep.
Yes, it's supporting the claim. So should his confidence in the theory increase, decrease, or what?
Mhm.
Increase, because he's pretty near to the mean, isn't he? He's not way out there near the tail. In other words, 0.13 is not that close to 0.015. It's not that close when you go to talk about the area under the curve. So you have to be a little careful about that. And 7, a researcher hypothesizes that the lowering in cholesterol associated with weight loss is really due to exercise. To test this, the researcher carefully controls for exercise while comparing the cholesterol levels of a group of subjects who lose weight by dieting with a control group that does not diet. The difference between groups in cholesterol is not significant. In other words, it's not in the red zone. Can the researcher claim that weight loss has no effect? He cannot, because you can never say that the defendant is guilty. You can only say that the data does not support the claim that weight loss is caused by exercise. You can only state it in the negative. You can never accept the null hypothesis. The defendant is never guilty. So you can't make that strong a statement, ever. Now finally, 8. A significance test is performed, and P is the probability of your test value, Drew. The probability of your test value occurring, and as a random choice. Why can't the experimenter claim that the probability that the null hypothesis is true is 0.2? Why not? You can you ever claim the null hypothesis is true? You can never claim that it's true. And even if you did want to claim that it's true, then the probability would be 80%, not 20%, agree? Because 20% is the reject zone. The p-value is the size of the red zone, isn't it? So,
Oh, yes.
so the p-value is the size of the reject zone, so the size of the acceptance zone is 80. So he's got it wrong in both ways. First, he can never say the null hypothesis is true, but if he tried it, then he would have to say that the probability is 80% if he went there. Okay? So the only thing he can really say is that if the null hypothesis is true, then we would have achieved our test result by random chance 20% of the time. We would have had this result just randomly, if the null hypothesis is true. So that's the only way that you can state it correctly. 9. For a drug to be approved, the drug must be shown to be safe and effective. If the drug is significantly more effective than a placebo, if the drug is significantly more effective than a placebo, so what you do is you test that it is equal to a placebo, agreed? You test that it's equal to a placebo, and your red zone is going to be the tail. And if it's in the tail, then it's significant because it's significantly different from a placebo. It's way off in that. So you reject the hypothesis that they're equal. Then the drug is deemed effective. What do you know about the effectiveness of a drug once it has been approved by the FDA? So this is a personal choice answer. So Ernie, if a drug is approved by the government, do you have confidence in it? If a medication is government approved, is it safe? Any drug, any medication. What's your personal opinion? Nothing to do with this course. If you go to your doctor and your doctor says, Ernie, the government approves this medication for you to take, is it okay? The government says it's good.
No.
Okay, well said. Okay, well said. So nothing is safe, true? Yes.
Sometimes okay.
That's right, you just take a chance. Okay, now what is a type 1 error?
It's a very small, we're talking about it is in the grade, the screen.
A little slower, I can't listen as fast as you can talk.
Oh, sorry. We'll talk about the red zone is when the difference of what you expected in the screen, in the Z, in the like when we draw with our when we drew the
You want to
graph,
draw?
no, when we drew the graph, and we found out that like in the reject zone, if it's extreme, that's when it's that one far away from the actual mean.
Right. But that's where we found our sample to be, in the red zone. So that caused us to reject. But are we always true? Is it always true that we should reject?
No,
When is it an error to reject?
if it's close to
Suppose that you and I both know that if we flip a coin 1,000 times, that we're going to get heads about 500, true? About half the time we're going to get heads. Now, if you flip a coin 8 times in a row, and you get 8 heads, then that's either says that our understanding of 50% is wrong, or you just had a fluky example, which does occur, but very seldom, agreed? So you can get 8 heads in a row, agreed?
yeah.
I've had it myself. Now, if you get 8 heads in a row, are you going to say that the odds of flipping a coin are no longer 50%?
No.
What are you going to say? That this is just a small percentage real-time sample, right? And that can be what happened. So if you get your 8 times in a row and you say, I reject 50%, then you have made a type 1 error.
Because it would be a screen log that I actually clicked that coin 8 times. If I do it again, I might not get that, it has again, not try.
That's right, that's right. So it could have happened naturally. It could have happened naturally, just very seldom. And if it could have happened naturally, but just very seldom, then you are not 100% sure when you reject the null hypothesis. Now you got it.
So it's almost like, okay, the 5%, let's say if the 5%, we're talking about first, even if there's 5% chance that you could get that, that result, but let's say 80% of the time, you might not even be getting that result, so you can say definitely that this is right.
Right. And in fact, if you do say that the null hypothesis is wrong, you know that there is a 5% chance that you should not be doing that. Because 5% of the time, you would have gotten that result naturally. So there's a built-in error. There's a built-in error. Good. Continue. 10. When is it valid to use a one-tailed test? So can anyone tell me, when do you use a one-tailed test?
When
When
it's not.
what is no,
When the claim states.
nothing to do with claim. Has everything to do with alternate hypothesis. You use a one-tailed test when, I'm going to give you 3 alternate hypotheses. H1, mu is less than 20. H1, mu is greater than 20. H1, mu is unequal to 20. Which of these 3 do you use a one-tailed test?
Well, the first and the second one.
First and second one. So you use a one-tailed test when the alternate hypothesis contains a greater or less than sign.
Oh, okay. See, when something's freaking like this, yeah, I can tell what it means, but when you try to put it in words, like what the question said, when is it valid to use a one-tailed test? I would definitely write that equation there and say if H1 is, if the alternative hypothesis is greater than
Greater than the established value.
Okay, the established point. So if it's less than that, that's when you need to still want to fill.
That's why we have class. Because if we don't have class, then you don't make the extension of symbols to words. And the world works in words. So
Yeah.
that's why this class is good. Because you expand what you can do. You can now do it with words a little bit. Okay? What is the advantage of a one-tailed test? Does anybody have an advantage for a one-tailed test? I'm not sure that I know any advantage. Do you?
Only one side has an error.
Yeah, but I don't see any improvement in that. So we'll see if anybody can find an advantage. Give an example of a null hypothesis that would be tested by a one-tailed test. The mean temperature is greater than some established value, greater or equal, mean temperature, anything of that sort, percentage of voters, all kinds of examples. Distinguish between probability value and significance level. Probability value and significance level. So p-value is the test result. It's the probability of your test result, agreed? That's your p-value. The significance level is alpha. It's the probability of the reject zone. So the p-value is the probability of your test result. And the significance level is the probability of the reject zone, alpha. That's what they are. So 13. Is it more conservative to use an alpha of 0.01 or an alpha of 0.05? Kayla, would it be more conservative to use an alpha of 0.01? In other words, by conservative means, we want to avoid a type 1 error, meaning that we don't want to reject a true null hypothesis.
So, 0.01.
0.01, your reject zone is smaller, isn't it?
Yeah.
So you're not going to make false rejections as often. However, now for the first time we come to a type 2 error. Type 2 error is the opposite of a type 1 error. So please remind me, what is a type 1 error?
That you reject the null hypothesis when it's true.
That's right. And then what is a type 2 error?
When you fail to reject the null hypothesis when it's false.
You fail to reject it when it's false. And you have this handout that I gave you, type 1 and type 2. So, Ernie, what does it say about a type 2 error? So it's in this lower left box. You find this diagram. Read the one on the lower right there. So you'll have this page. Print it out. Yes. Next page. One more. Okay, read this. Read that one.
Type 2 error, failing to reject false null hypothesis.
That's it.
Failing to reject the false null hypothesis.
Now, it's given the symbol beta, just like a type 1 error is given the symbol alpha, right? It will occur with a probability of beta. But beta is not 1 minus alpha. Beta is hard to calculate. So beta is the probability beta is the probability of making a type 2 error. We don't have any numbers for beta. But now let's address this question. If you go to an alpha level of 0.01, will you increase the probability of a type 2 error? Will you increase the probability of a type 2 error if you go to a smaller reject zone?
Sure.
True. You guys got it. You see it. Absolutely right.
Plus,
Yeah, you got it. Okay, good. Now, next question is, what's the next one? I stopped. No, I got another page. 14 skipped, right, 15. An experimenter which expects an effect to come out in a certain direction. Is this sufficient basis for using a one-tailed test? Why or why not? Kayla, why or why not? Now this goes back to James Bond. Should we have used a one-tailed test or a two-tailed test on his ability to identify drinks? Two-tailed, because he might have been able to identify them but just been confused about which drink was which. So you use a two-tailed to uncover unexpected information, true? unexpected information is recovered.
Well, for this sentence, isn't it a bias, the way he, I mean, if you expect an outcome.
Enunciate. Sometimes your words, I don't get the,
Oh, I'm sorry,
Yeah.
isn't his, bias, like,
Yes.
for him to be, they said, see, the experiment that expect an effect to come out in a certain direction? If he said, if that's what he want, and isn't it in bias in your experiment?
it is, very good, it's a bias. It is very good, you're right, he's putting bias into the experiment, and he's not being neutral to start with, that's a great way to say it.
We'll use the two-tailed so we can find out unexpected information.
Yes, just as Nooks is saying, you don't know what's gonna happen, it's not your, you didn't design the universe. 16, how, did we do that one? No, I'm glad we skipped it. A two-tailed probability is 0.03. What is the one-tailed probability if the effect were in the specified direction? The two-tailed probability is,
We have 16 now.
Who got 16?
you have 16?
Yeah.
I didn't want to do it. Okay. How do the type 1 and type 2 error rates of one-tailed and two-tailed tests differ? Okay, anybody want to handle that?
The top one is the alpha,
Yeah,
and then top two is the beta.
that's right.
And I think the difference with, top two, you will end up rejecting, because on previous question 13, if the beta is higher, you enter, reject on false claim.
Right, but is this different on a one-tailed or two-tailed test? Does it make a difference whether you have a one-tailed test or two-tailed test?
That should be the, the top one.
Well, they do differ because they ask you, how do they differ?
Test.
The error rates.
Oh.
I myself don't see how they would differ. Yeah, well, that's why I didn't answer the question, because I didn't see the answer. I'm not sure either. There's something there that I don't know about, because Lane is indicating that he's aware of some difference.
I think the error will be for top two, it will be higher.
For one-tailed or two-tailed?
Both of them.
Well, it's not a question. Nope, I don't see any difference. Okay, on to 17. A two-tailed probability is 0.03. Now,
If it helps, it's not one of our questions.
17?
No.
Okay, well, I thought it was. Good,
Just
okay.
curious, we use device, let's say two-tailed, and the parameter is 0.3.
It would be 0.015 in each tail.
Each tail.
That's right. So the one-tailed probability if the effect were in the specified direction would be 0.05. And if it was in the other direction, it would be 1 minus 0.05.
They won't be negative, won't be positive.
No, it would be 0.03. B, what would be the effect if it was in the other direction, 0.97, okay? In other words, 1 minus that, 1 minus 0.015, okay? Yes. Yeah, that's right. Okay, 18. You choose an alpha level of 0.01 and then analyze your data. What is the probability that you'll make a type 1 error given that the null hypothesis is true? It's a very good question. Answer is. Let me give it to you in our familiar terms. Suppose you choose an alpha of 0.05, as we usually do. What's the probability that your random sample was in the reject zone naturally? 0.05, agreed?
Yeah.
So what is your probability of making an error? 0.05, 5%. Now, if you go down to a 0.01 reject zone, what's your probability of making an error? 0.01, right? 0.01, just the same. But now Lane brings out a very cute point. B, what is the probability that you will make a type 1 error given that the null hypothesis is false? 0. Because if you know the null hypothesis is false, you can't make an error when you say it's false at all. So he's just playing games at that point. But that's what he wants. 19. Why does it make sense to test the hypothesis that the sample mean is 42? Can you test the hypothesis that the sample mean is 42?
No.
You test the hypothesis that what mean is 42? Right, because you know the sample mean is 42. So he's playing games with words again. Okay.
So, you already know the mean, you can test it.
Yeah, exactly. That's another way of saying it, yeah. In other words, you're supposed to test the population mean. You're not, so you use the sample mean to test the population mean. So you don't test the sample mean. You test the population mean. Okay, Muscat? Clear? 19. Okay, 20. True, false. It is easier to reject the null hypothesis if the researcher uses a small alpha value. It is easier to reject the null hypothesis if the researcher uses a small alpha value. False. False.
It's easy to reject the null hypothesis if the researcher uses a small alpha. What is it?
Saying that the red.
Okay, here's 5%. Reject. Here's 1%. Reject. Which one of these reject zones is more likely to capture your sample data?
It's 5%.
5%. Your sample data is more likely to fall in this reject zone than that reject zone, agreed?
Sure.
So this is easier rejection, because your sample data will naturally fall into this reject zone more often than it will naturally fall into that reject zone.
So when it says smaller alpha, I think it was 0.1, which is a small.
Yeah, this is 0.1.
Oh, 0.1 is bigger than 0.5, so 0.5 is smaller.
No, 0.1 is smaller than 0.5.
Then what I'm saying is, it's easier to reject the null. If
So this is a false statement.
It's smaller. Oh, it's a false statement.
It's a false statement. It's a false statement. 21. 21. You are more likely to make a type 1 error when using a small sample than when using a large sample. Let me give you a way to approach this. Suppose your sample size was equal to the population size. Are you going to make a type 1 error?
No.
No. Suppose it was 1 less than the population size. You're going to make almost no chance of a type 1 error, agreed? So the larger your sample size, the closer your sample comes to the population, so the less chance that you are making an error. Okay, 22. You accept the alternative hypothesis when you reject the null hypothesis, yes or no? But you have to read Lane to know this. And it turns out to be true, that if you reject the null hypothesis, then you are accepting the alternative hypothesis. If you reject the null hypothesis, we're accepting the alternative hypothesis. Triola's a little bit more wimpy. he says you support the alternative hypothesis. But Lane's bolder, he says you accepted the alternative hypothesis. Okay. 23, you do not accept the null hypothesis when you fail to reject it. That's a big time one, and the answer is, can you ever accept the null hypothesis? You can never accept the null hypothesis. The defendant is never innocent. True? What are the only two things you can do to the null hypothesis?
Support it.
No. You reject it or
You fail to reject.
fail to reject it. That's it. That's all you can do. Reject or fail to reject. If it's in this zone, you reject. If it's in that area, you fail to reject. So if it's here, if your sample is here, you reject. If your sample is there, you fail to reject. You never accept. Okay, and the last question. Last question. 24. A researcher risks making a type 1 error anytime the null hypothesis is rejected. This is Lane being cute again. Hint, suppose the null hypothesis is known to be false. If the null hypothesis is known to be false, is he risking making a type 1 error?
No.
No, so we have to go false on this, but that's just Lane being cute. It's not a real statistics question. Okay, so we went through Lane, we went through quite a few of sample Minkowski problems, so now the ball is in your court. Go. Okay, I've got a suggestion. Let's go to Ilkowski problem 48. Ilkowski problem 48. I'd like you guys to both do it on the whiteboard. 48.
Who wants to do it here first or just directly on the website?
Depends on your guts. Depends on your courage. Or what you're comfortable with. Can you use the one back there by Lynn? Here, you just do yours right here. Let me turn it before you do. Okay, and we try to share yours. Kayla, I'm gonna move your board, okay?
Okay.
Okay, let's try that.
48, all the various parts.
Can you move your board, please? Okay, got it.
So first we have to do the claim and then the unpaid claim, and then from that we can answer which one is now and which one is after. So we can say the claim. So this is B now. So claim is this
Oh,
one.
great.
Claim, yes.
HC.
Oh, not yet. We can say that the claim is H0 when it has the equal sign. So whichever has the equal sign, then it is the H0. So first claim is that this one. The population mean time and get to be 15 minutes.
15 minutes.
Yes, so that's how it's going. So you write this one, line this one. The population mean time.
15.
The population, and you write this one. This one, the population mean time. So the population mean time, and get the So now the unpaid claim it's mu is equal to 15, right? Mu equals 15. This one is not equal on the column. So now we know H0 is gonna be the one that has the equal sign. So H0 is mu equals 15. And then H1 or H1 is this one.
This way?
Yes.
Oh, this way?
So that's your answer. H0 No, H mu is equal to 15. Not equal to 15. So is this right field, left field, or two field? When you have this equal sign and not equal, this the H5, it will tell you if it is right field, left field, or two
Yeah,
field.
that's the one.
If it is less than, then it's left. If it is greater than, then it's right. But when it is not equal, then it's two field.
No, you've gone astray. You've gone astray. Let's go back and talk to Taylor. Come on.
So this one, two
Okay.
field.
Can you interrupt for a second?
Mm-hmm.
And can you talk with Knox about
So what
why you
symbol
did A, B,
represents
and
the
C the way you
random
did?
variable it is?
So, A, is the test one of mean or proportion?
The x4. That's simple. X4 for the mean, x4 for the random.
Do you want to read mine later? That might be why.
This
Because
is
mine's
this
is-
one, this one.
I run this over your self copy. You aim to the main map all the time.
And then
Therefore,
variable
it's,
for
so
this
it's
one.
Mm-hmm.
Okay.
The
then B. Stick the note in stick the note in alternative
This
boxes.
one is this, but the
So,
population standard
claim
deviation, no?
Proportion mean is 15.
No, right? Not the nine. So this one
Standard deviation 6.5. Con una posición sostenida population mean town on therefore would like to be 15.
This is
So
just a
that's the
sample,
claim.
right? I
Would like
random
to be
survey.
15.
But the
Proportion is,
population, no, so,
and
no.
the claim population is not 15 years. So,
So calculate the
Okay, so-
following, so x bar,
So if it is 15, it's
It is
equal,
X
so it's
one.
not 15.
that's okay. It's okay.
Because it doesn't say,
Yeah, that's what
Equal.
it is right here.
Mhm.
Right, variable is the sum.
Okay, so Knox, 17.4 is your sample mean. Is your sample mean, okay?
Yeah, 7.4 is the, okay, for
It's
entire
a sample
population.
mean. But what they wanna do is test the population mean, and the population mean is what you're going to test. So conduct a hypothesis test to determine if the population mean time is 15 years. So 15 is not, 15 is the mean that you're testing, not 17.4. So you got your number wrong there. You need a 15, no, you're right, but on Knux's board and the front
Yeah,
board, you need a 15, not a 17.4.
If you do not know the standard.
Good, okay, continue with that.
T, so the T,
T test, and this is the population,
not the
right?
Z distribution, right? T test, because you do not know this one. Only the T distribution. Awesome.
students T
Yeah,
distribution.
yes,
Oh.
same, student.
Mm.
Oh, 'cause you're testing
Now
this
find
one.
the p-value. So let's find the p-value. It's equal to, maybe gotta have the formula. You have the formula here? It's
Can you write down the
x-
general formula for a
X bar
T?
minus,
test? T, oh, way over in the right here. Let's try, no, this is over right. So let's write down T equals X bar minus U over.
so,
P?
yeah, so,
Now, check your numbers one more time.
So it
T?
would be
Yeah.
17.
It would be,
T
yeah.
Because you're testing to see if it's
X
15.
Yeah,
bar
you got it. That's why it's good to write
minus
formulas
U
down.
all over.
Oh.
S, and then over root and
Good.
square root of n. Formula. So, we have this one. So,
X bar.
Sir, when I asked for which test would be used, is it saying that?
Just a second, let me watch. Okay, now, moving up, you got a question? Sir?
No, I also want to ask about which test would be used, is it a two-tail test, like a one-tail test?
What's that?
That's two-tail.
That's two-tail test.
I was confused with the C distribution, and the T distribution on the.
No, it doesn't matter the tails. The tails comes only from that. From that. As soon as you see that, it's two-tailed.
When I say which test should be used?
Which test?
Yeah.
Well, by that they mean T-test, well,
My next question is
what
which
test?
distribution?
Oh, I see. Do you wanna use the P-test or the, T-test? You wanna use the critical value, you wanna compare Z-values, or you wanna compare probabilities? It's your choice, really.
Oh, that's what I said for, like which test?
Yeah, that's the nearest I can make up that she's asking. No, this is not a two-tailed test, that's not what they want.
Oh,
I don't think it is, because they already guessed that up in C, right?
yeah, God, they say two.
Right, so what they want here is, do you want to make a P-test? Do you want to make a P-test or a critical
So
value
divide this
test?
one, 6.3 divided.
In other words, you want to compare the probabilities, or you want to compare the P-test? Okay, good.
6.3.
Go ahead, state the distribution, T or Z? So that's the T-value. Now you gotta find the probability that matches that. Let me get my table and see what I get. Okay, we got 5 minutes.
So 2.4 divided by this one.
So you have 74, and you have a big number here. So, see, it's off the charts.
Yeah.
So what you're gonna do is just say,
So now, it's
say something like 5 or something like
So
that.
alpha.
Or say 3, just say greater than 2.6,
Just
right?
0.5, because
Say
it does
greater
not
than
say.
2.6. So
Alpha
that's why
is,
your table goes up to the other
just,
picture.
say,
Greater than 2.6.
alpha is
Okay,
0.5%.
and, no, greater, no, it's over here, so it's, you read the probability up here.
0.05.
Yeah, it would be.
So it's less than 0.01.
Yeah,
Less than, see, it's less than this, it's a two-tailed test, right? So less
Yeah.
than 0.01,
and here
less than the other one.
0.02.
Less than 0.01.
Less than 0.05.
Point.
Huh.
With a
So now,
calculator.
you
Just
look
that
up
one.
table.
Oh,
Just a second,
That's
right
the, look up
That's the
table.
p-value.
Yeah,
Decrease.
p-value's up at the top here,
And you have to find it on this one since, okay.
so it's less than
I know,
0.01. Next question.
T.
No, I'm trying to get the formula for
Okay,
did.
you got it.
So that's the P value.
Now, your alpha value is 0.05, right?
N.
So your alpha over 2 is 0.025, right?
N is equal to
Since
75.
it's a two
So
tail
degrees of
test,
freedom,
so
N minus
it's the
1,
same as
so
alpha
74,
value.
so go 74. Or 70.
74.
Alright, 70 is 9.
Mhm.
So, it's a 2 tail, and 0 to 5, so,
N minus 1的话
alright, so 74.
75 minus 1会74。
Yeah, but then this one only gives 70, so
75
just take that one.
Okay.
So now find,
70
okay, so it's a 2 tail, so 0.025. So this number
So
should
this
be
is less than that, so.
too big, this
Yeah.
one.
70
Yeah, so this one too big, so,
This is another before.
あ、はいはい。
so it's, so let's draw our graph. So it's maybe, it's,
Good. Reject the null hypothesis. Why?
it's up here, right? Because this one alpha 0.0001. So so this one is the smaller.
Very
than
well
this
done.
one, right?
Mm-hmm.
And now
So
for the
you-
gold
we
ring,
reject.
go to Triola's flowchart and state your
So,
conclusion. And lawyer,
So you said you
Ease.
reject this B is up here. And your alpha 0 to 5. So you reject, so not you reject. What zero is, yeah, so you have 70 and but then this one is still the same. So not really this one, but smaller, even smaller number. So even smaller, and your threshold is this one. So this one
Very
is
well.
bigger. So
okay.
we say you reject. So you have the other flow chart. The this week flow chart. This week.
Nice job, Kayla.
Thank you.
Hey, Ernie, you wanna take a look at what the lady did?
Same.
Take a look here.
So you get the same and just round off. 3.3. So if you go here, it's less than this number, 70, and it's 0.01, right? For one total. So it's 2.6. But then your value is 3.3. It does not even show here. So it's less than this one. So you have to reject. Okay, mas kami sa pagkakas. So it's less than. So reject, then you have your chart this week. That you this one, that one. Hi. So, we reject the null hypothesis here. So the original claim contained the condition of equality.
Yeah,
So,
isn't it testing at the
the
population
yes,
units?
right, it has equal sign.
If
the equal sign.
Reynolds
applying
Sylvia
to
seventy-five, right? We're
It's
gonna
new
do
equals 15,
one
right?
17.4, I
So,
thought what's
yes.
your mean?
So, yes,
I thought that was supposed to be
do you reject
the mean
the
made now.
non-hypothesis? No,
It's not,
Yes,
it was
we reject.
sampling.
So you go,
So
yes,
it's saying,
so there,
I was asking,
So,
what's the probability of
so you
getting
write this,
this number
there is
if your
sufficient
sample mean
evidence
is
to
15?
warrant rejection of the claim.
I mean, your
without-
population.
X by is the
Sample mean.
sample mean,
So
right?
you write
And then
this
the
one.
mean here is what is it,
So
by your mean.
this,
Yeah, because they're testing the.
Kelly, you forgot part E.
part is sufficient.
Your part D, your answer to D should be X bar.
Evidence
And X bar is the mean of the sample.
warrant
This is,
rejection
this is mean.
of the claim.
D here. There you go. So, that confused me too, but it's saying that,
So now we go here.
what's the probability of getting
The
this
claim is
sample
this one,
mean
right?
of
The population
17.4 if the population is 15 years?
Population.
So they said the population is 15, which is new, and you're testing it against the 17.4 was what you got. So this, your sample mean is 17.4, and they're asking, what's the probability of getting this sample mean if it is in fact 15 years? And that's why you use 17.4 here as your sample, and then this as your population, because you're testing how likely is it to get 17.4 using 15, and it's not. So if you got 17.4, it wouldn't be 15 because it's too small
This one is,
based on
the answer is,
the p-value
Right
Yeah,
here.
yeah, okay. This is
Okay.
okay,
You got
yes.
3.29,
Hi.
Yeah.
okay.
So
It seems like that in,
decision
even that they,
Oh,
if you,
reason for
Switch it?
decision.
yeah, you still
Really?
got the 3.99.
It's,
So when I look in the chart, it's not
so,
listed.
Yeah,
So,
alpha
it's not listed there, then what
point
you,
zero
that's what
five,
you
right?
should.
But then our,
was that, I did that, I
it's,
got
less than
3.299.
0.01.
Yeah, so you got pretty
But
much,
then,
yeah, you got a negative, but, and
why
it's
not
a,
negative?
this is,
Just
3.299